Let's talk about now how we can represent any stationary invertible ARMA model as an infinite order MA or a GLP. So previously we looked at how to do this with an AR. We have an AR to MA or a GLP, generalized linear process, using this long division or using psi.weights.WGE. So if we have just a simple AR2, then we can of course write it in backshift notation such as this, and then we could do the polynomial long division on it, or we just have psi.weights.WGE because the long division gives us the psi weights. So we have our phi is positive 1 phi 1 positive 1.6. We can see here phi 2 is negative 0.8. We have that right there. We can tell it how many lags. Thus, this is potentially an infinite order. So this could go out for an infinite number of coefficients. So I have here approximately, but those are just the coefficients. Note here though that psi naught, psi sub 0, the first psi weight, is always 1, and that's not printed out here. So we can see that here. This is 1, and then these are the rest of the coefficients, and they're just the coefficients of the with the backshift operator here. And so that when we operate that on AT, we end up with AT times 1 is AT, and corresponding B times AT is AT minus 1, so on and so forth, all the way to AT times B to the fifth is AT minus fifth, and we've represented the AR as approximately an MA5 here. But this quality goes out to potentially infinite number of terms. So how could we do that with an ARMA model that would have something something over here in the MA side? So let's look. So this is the same AR side, but on the MA side we have a theta 1 here of negative 0.9. But if we want to represent that as the GLP, all we have to do, we'll just change it into backshift notation. And using the same function, we can say this is approximately, we got psi.weights.WGE, and there's our phis, that's the AR side, there's our thetas, that's the MA side. Note that that is a negative theta 1, so we have it here. I take it out, this time I'm going to take it out just to show how this works. Lag.max equals 6, and so I've got 1, 2, 3, 4, 5, 6 coefficients, and doing the same way there, we've got, okay, this is xt now, equals this function of the ATs, and that is an approximate GLP form. And if I distribute that AT, then we'll have AT times 1 is AT, AT times 2.5b is 2.5 AT minus 1, all the way down to AT times this coefficient b, the sixth, is 0.28672 AT minus 6. And that is how we can represent an ARMA model as an infinite order MA, or as a GLP. Using very quickly, we could have used polynomial division with this, and it would have worked out the exact same. But we can use psi.weights.WGE too in order to get those psi weights. So great job. See you in the next one.
Now let's look to see how we can turn an ARMA model into GLP form.